to this second podcast on electroanalytical chemistry. And in this podcast, we're going to focus on a discussion of cyclic voltammetry. I will then stop the podcast, and there'll be a third podcast that will focus on discussion of the hanging dropping mercury electrode and on its use in stripping voltammetry. So let's get started. If you'll recall last time, I introduced the idea that all electrochemical methods are categorized based on Ohm's law. Either you perturb the potential of the system, or you perturb the current in the system. When you affect the potential, it's referred to as a controlled potential method, and when you affect the current, it's referred to as a controlled current method. We use two different devices in order to affect these experiments: a potentiostat in the case of controlled potential method, and a galvanostat in the case of a controlled current technique. Today, most electrochemists own electrochemical workstations which are capable of functioning both as a potentiostat and a galvanostat. Last time we talked about two examples of controlled potential methods and two examples of potential step methods. These were chronoamperometry and chronocoulometry. In both of them, at some point in time, marked here as T0, the potential of the system is ramped between two potentials, E1 and E2, between which the redox potential for your analyte should be. And as soon as you have instantaneously changed that potential, current will flow. You'll either be oxidizing or reducing that material in solution. Originally, you'll have whatever the bulk solution concentration is available for oxidation or reduction, and as you begin to oxidize and reduce your material, of course, you will decrease the concentration of redox active species near the electrode, and so the current will die away. And that plot of current as a function of time is what you measured in, or we talked about, is what you measure in chronoamperometry. If you'll recall, the current had a t to the minus 1/2 dependence, and it's very unfortunate, but what's most important is the current at the point at which you change the potential instantaneously, and we discussed how it really isn't possible to do that in a practical way, and so your experiment is a tiny bit flawed, and that's the reason that we have chronocoulometry. Is if you integrate the current as a function of time, what was a minus for the chronoamperometry experiment becomes a plus for the chronocoulometry experiment as the charge builds over time. So the signal that you care about that's most reliable is near the end of the experiment, and it's a very large signal in the case of chronocoulometry. Both techniques very useful in terms of quantitating materials, so you can determine concentrations of analytes, and they've been very widely used. Today we're going to focus on controlled potential methods again, but we're going to focus on a potential ramp technique, and that is cyclic voltammetry. And the difference here is that instead of stepping the potential between two limits, this time we are going to ramp the potential at a set rate, dE dt, we call scan rate, between E1 and E2. And just as in the potential step techniques, it's really important that the redox potential be poised somewhere between the two potential limits of interest. Now, what we're going to do is we're going to keep the solution quiet, and that's important in terms of our mass transport. Mass transport needs to be diffusion limited. By keeping the solution quiet, or quiescent as we usually describe it, we can avoid the onset of natural convection or unnatural convection. And if you recall, these are always very rapid experiments, so the time for measurement is kept relatively short. Lastly, we avoid any problems from migration by adding significant amounts, relatively high concentrations of good electrolyte materials. And this decreases the contribution from the analytes migration to the electrode. The bulk of the migration current ends up being attributable to the electrolyte. So that's the experimental conditions for carrying out the experiment. And what we're going to do is we are going to measure, in this case, the current that flows as a function of potential. And the characteristic waveform for voltammetry, which is often referred to as a voltammogram, appears at the bottom of the slide. Now, I would be remiss before we actually discuss the waveform itself if I didn't present to you the fact that there are two different conventions for the axes on a voltammogram, the American and the European conventions. The European convention is presented to you on the right-hand side. The focus is on probing reduction processes. And so you have cathodic potentials appear to the right and anodic potentials appear to the left on the x-axis. And you plot cathodic current above the axis and anodic current below. So the upper right quadrant ends up being where you see reduction, and the lower left quadrant is where you see oxidation. Now, American conversion, literally upside down and backwards. So the American convention places anodic potentials to the right, cathodic potentials to the left, and plots anodic currents above the axis and cathodic currents beneath the axis. And the net result is that oxidation appears in the upper right quadrant for American voltammograms, and you will see reduction current in the lower left quadrant for American. So you've seen both. Pause when you read a paper, make sure that you've oriented yourself properly, and you should feel pretty comfortable about dealing with them. So now let's actually look at the voltammogram, the shape of it, discuss its appearance and the information that we can pull out from it. So the top of the slide is showing you one cycle for a voltammogram, means going from E1 to E2 and back again. And we call the rising portion the forward portion of the waveform, and the falling portion the reverse portion of the waveform. On the response, the curve, the top portion of the curve going from E1 to E2 that has a peak that's labeled EPA, that's the current that flows under the American convention in response to increasing the potential between those two limits if the redox potential for your material falls somewhere in between. So I want you to think about what's happening at the electrode surface with me. So we start out the experiment at E1, and your material is in its, we'll say, reduced form. And as we move to more and more positive potentials, once we exceed the redox potential for the system, all of a sudden now your material will, assuming it's kinetically able, will be thermodynamically able to be oxidized. And you'll see the current rise to a peak. It rises to a peak and then it falls. And the reason it rises and then it falls is initially at the electrode surface, having come by diffusion control, you have lots and lots of R, the reduced form. As soon as it comes close to the electrode surface, assuming that it's kinetically favorable, and we've said it is thermodynamically favorable, then R will get oxidized to form O. So you'll start to have a lot of current flowing. How much? It's proportional to the concentration at the electrode surface, so you're going to see a lot of current flowing. But now, as time begins to pass, you're going to start to deplete the R that was originally available near the electrode surface. So the current will peak, the oxidation current will peak, and it will now start to decay, reflecting the fact that near the electrode surface you're starting to form a lot of O and you don't have so very much R. And it will only decay so far. How much depends on what E2 is, but now you're at that uppermost potential limit that you've chosen. Now if you choose to continue to change the potential and go back to E1, you're headed between, you have the oxidized form and you have the redox potential somewhere in between E2 and E1. No current will flow until you pass the redox potential. As soon as you do, all of that O that's now near the electrode surface that you've produced by oxidizing R, all of that will now start to become R again. And so you'll see a lot of reduction current flow, and so the current will go down. It goes down because it's in the opposite sense. You had oxidation current, had one sign, and now where you've got reduction current, it'll have the opposite sign. So the current will go down, 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 down. And then again, as you start to deplete all of the available O, you're starting to now only have R near the electrode surface. Again, the current will start to decrease and it will move back to the original level that it had at the start of your experiment. So net result is you produce this characteristic waveform that some electrochemists informally refer to as the duck, and it has two peaks. One peak corresponding to the production of maximal amount of current from oxidation, and the other peak due to reduction. Those are referred to respectively as E-peak anodic and E-peak cathodic. The current that flows we refer to at those 2 points as I-peak anodic or IPA and I-peak cathodic, and they can be sampled as shown from the voltammogram. And most modern potentiostats will allow you to actually extract this information directly using your computer. Now, in an ideal voltammogram, one that has been obtained for what we refer to as a reversible system, you're going to be able to extract some important information. So we need to talk first about what it means when we are talking about a system being Nernstian. What's the significance of that? Because that's the magic word we're going to talk about. So Nernstian means that it obeys Nernst equation, and we've seen that before. E equals E naught minus 0.059 unit of volts divided by N, a number of moles of electrons, times the log of Q. Well, in this case, the log of Q becomes, if we're talking about the reduction of a material, O going to R, it'll be concentration of products, R, concentration of R, divided by concentration of reactants, or concentration of O. So that log term is the ratio of the concentrations of the two different redox forms of the species. Or, as shown on the slide, if I move E naught to the left-hand side of the equation, E minus E naught equals a constant minus 0.059 divided by N times the log of this concentration ratio. So now let's talk about the significance of the potential that you apply and how it relates to the redox potential. We can either be below the redox potential or we can be above the redox potential. And what we want to think about or see is, what does that mean in terms of this ratio of concentrations of O and R? So first, let's think together, what does it mean if E applied is greater than E naught? Well, then that difference is always going to be positive. And if that difference is positive, note that I have a negative sign on the right hand side, negative 0.059 times the log of that ratio. Then it means that that log ratio has to be negative. And for that log ratio to be negative, it means that R has to be a lot smaller than O. And if R has to be a lot smaller than O, it means current must have flowed in order to oxidize the material. So oxidation is occurring. Now let's think about, well, what does it mean if E applied is below the redox potential? Well, if E applied is much less than E naught, then it means the difference between E applied and E naught must be negative. And if that difference, that term on the left, is negative, again, noting I have a negative 0.059 times this log term on the right, means that log term must be positive. And the only way that log term can be positive is if the concentration of R is much greater than the concentration of O. And again, the only way it can get to be that way is if O is being reduced to form R. So what does it mean? It means that reduction is occurring. So the key piece here is that when you're varying the potential, varying E applied, what are you doing? Potential excitation is controlling the concentration of O and R in solution. You have direct control. All right, so with that background, Nernstian process is really exciting because we have the potential. If a system is Nernstian, that means it will behave according to the Nernst equation, and it's going to give me the ability to extract some important information. So in cyclic voltammetry, we look for certain characteristics. We look to see if the system is diffusion controlled, and that's listed in the center, or if IP cathodic and IP canonic are proportional to the square root of scan rate. And you'll often hear this referred to as Randall-Sevcik behavior. But if that plot is linear, then that's evidence the system is diffusion controlled. We look to see if E peak is independent of scan rate. And one way of doing this is simply to look and see if the difference between EP canonic and EP cathodic is a constant. And it should ideally, if it's Nernstian, be 59 millivolts or 0.059 volts divided by N. That's from your Nernst equation. So we look to see if it's independent of scan rate. And the last characteristic is we look to see if the peak current at EPA is the same amount of peak current that we see at EPC. And if it is, if the ratio of IPC to IPA is unity, then it means your system is chemically reversible. So if those criteria are met, then you have permission to add together the two peak potentials divided by 2, and that is your redox potential. Very exciting. So this is one of the key strengths of cyclic voltammetry, is that under certain experimental conditions, depending on your system, you can extract redox potentials for your analytes. Very exciting thing. Now, not every system is reversible. In electrochemistry, equally exciting is the fact that they aren't. And they can be what are called quasi-reversible or irreversible. And so I want to show you some examples of both. Quasi-reversibility tends to be characterized by a delta E peak which is greater than 59 millivolts and which varies with scan rate. So if delta E peak increases as you increase your scan rate, then you're possibly dealing with a quasi-reversible system. But there are some other situations that can basically masquerade as a quasi-reversible system, and an IR drop in solution, if you're working with, let's say, an organic solvent and you've had added electrolyte to it, it's a fairly resistive medium, and so that IR drop can sometimes masquerade as quasi-reversibility. So you have to think very long and hard about the system that you're working with and make sure that you've set up your experiment well and properly. The second behavior is irreversibility, and irreversibility isn't necessarily a bad thing, but what it means is that your system either can be oxidized or it can be reduced, but it can't undergo both processes. And why not? That's because either the product isn't redox active, or it might go on and do some really cool chemistry. And how do you distinguish an irreversible system from a reversible or quasi-reversible one? Well, it won't look like the duck. It won't have a return wave. It'll look like half a duck. And if the system is uh, on the borderline of being irreversible, if you have very slow electron transfer, the two redox waves for oxidation and reduction just won't overlap. So it'll look like a misdrawn duck. So let's take a look at both of these. In bioelectrochemistry, biomolecules tend to fall in the category of being quasi-reversible. Why they do that is a consequence of the fact that they have a characteristic shape and a characteristic very large size. And they've been designed by nature to avoid undergoing spurious electron transfer with other biomolecules or reagents inside of the cytosol or wherever it is that they live in an organism. And so on this slide you're looking at voltammogram for microperoxidase, which is a digestion product of cytochrome C. And what you want to see is that there are 5 voltammograms here representing different scan rates. The highest, largest one is the fastest scan rate, and they scale downward to very, very slow scan rates. You'll see some blue asterisks on the left and on the right, and they're intended to mark the 2 points on the left and the right where all of the voltammograms overlap. And when you see that, that's evidencing really high quality experimental work in order to see that ISO point. But that ISO point's important because what it tells you is that there's 2 species, an oxidized species and a reduced species, that are interconverting. And if you look up with your eye straight up and straight down, you will see that delta E peak is not a constant. It's increasing as a function of the scan rate, and that is evidence for quasi-reversibility. And my little arrow here, I hope, helps you to see that it's really on a sloping line, and so the delta E peak is really increasing with scan rate, which is a quasi-reversible system. On this slide, I wanted to give you another example from biochemistry of a system that doesn't undergo reversible voltammetry. So the small amino acid cysteine, L-cysteine, shown at upper middle, it can be oxidized. It can lose 2 protons and 2 electrons. And when it does, it tends to form this dimer product, cysteine, which is shown at right, has a sulfur-sulfur bond, and that is irreversible voltammetry. And so I have shown you at upper left 2 voltammograms recorded at 2 different kinds of electrode substrates. The top one is boron doped diamond, a semiconductor, and the lower left is glassy carbon. Glassy carbon is an amorphous form of carbon that tends to be a good electrode substrate for biomolecules. And what you can see is you get a very ill-defined oxidation wave at glassy carbon, but a sharper and more well-defined redox wave at boron doped diamond. But in both cases, all you see is oxidation current, and that's the peak on the top. And you know it's oxidation wave at top because the potential is going from 0 to 0.8 volts on the right hand side. So you're going to larger, more positive potentials. You'll notice there's no return wave, and so that's showing you that when you have oxidized the cysteine and formed cysteine, you can't, it's not reversible from an electrochemical standpoint. Kind of cool. Something else that's really cool about voltammetry is again given based on not having perfect redox waves. You can actually begin to get insight into complex reaction chemistries. You can generate intermediates that are interesting, capture them, stabilize them, probe them spectroscopically. You can follow their kinetics, things again that are very unstable. And on this slide, I just want to show you an example of this. So electrochemists will refer to complex mechanisms based on steps that are either electrochemical in nature or chemical in nature. So a common electrochemical mechanism is EC, where you either oxidize or reduce something, and then that product does chemistry. And so I'm showing that to you underneath EC mechanism. First, you have this material R, it loses an electron, means it undergoes oxidation. The oxidation product O then undergoes a reaction with a rate KEC to form some material Z. And if it's not possible to go back from Z to O, and if a Z is not redox active, then depending on how fast KEC is and how fast your scan rate is, your voltammogram will look different from the way you might expect it to look. So if you have a very slow rate for this second chemical step, then you won't form a lot of Z, and when you change the potential, do the second half of your potential sweep, go back in a reducing sense, then you'll be able to reduce O to R, and so you'll see something that looks like a voltammogram. On the other hand, if KEC is really fast, then you won't have any O to re-reduce, or very little of it, and the voltammogram will look more like the curves in pink and in red on the graph at right. So, and you can actually use those data and vary the scan rate and figure out the reaction rates, which is really cool. You can do this with programs. An example of that is DigiSim, which is a product of Bioanalytical Systems, and it's good in terms of bioanalysis, and I've given you a reference to it. So one last thing I want to talk about in regard to voltammetry is you have this duck, this odd shape of a waveform. And it's not the ideal waveform for quantitation, because as you go to lower and lower concentrations, it's going to be harder and harder to measure the peak current relative to the background. And so one trick, or one way around this problem, is to move to smaller and smaller electrodes. And when you do that, you actually change the mode of mass transport from what's referred to as planar diffusion to radial. So in this slide, I want to show you that. So if you consider an electrode that is really, really small, and you start to think about the size of your molecule and its perspective in terms of moving to that very, very small electrode surface, if you use a fairly standard, relatively slow scan rate, then your analyte will move using radial diffusion, the mode of mass transport that's shown on the right. And there'll be a different mode of mass transport, and therefore a different response waveform, which I'll show you in a second. If you scan really, really fast, you can change the mode or the appearance of the mode of mass transport. It'll look more like what you would see for a macro electrode, like the one you used in lab, a 1.6 millimeter electrode. The mode of mass transport will be planar diffusion. So you can move, if you use very small electrodes, you can change the mode of mass transport. And with that change of mode of mass transport, you can actually change the waveform shape. So on this slide, you're looking at two voltammograms, or two sets of voltammograms. Both are for compound referred to as ferrocene. I mentioned it to some of you in lab. This is 2-cyclopentadiene sandwiching an iron 2. And that iron 2 can undergo oxidation to an iron 3. So it's that iron 2, iron 3 that is the redox couple in ferrocene. Very stable compound, and it actually is used as an electrochemical potential standard in solution by the International Union of Pure and Applied Chemistry. Well, if you use a microelectrode, a very small electrode, then the ferrocene will move by, as I said, this radial diffusion to the electrode surface, and you'll see the waveform, the voltammogram, shown it right in red. It looks a lot like a step, like a plateau, or if you will, an acid-base titration curve, and it's very easy to measure the current due to that curve. You just literally drop a straight line down to the x-axis, and that peak current will scale linearly with the concentration. And the response waveform is shown in green, or the current dependence is shown in green on left. If I scan the electrode really rapidly, I could actually produce a waveform that looks like the waveform shown in blue, or the series of waveforms shown in blue. Those are actually for a macro electrode, but I would produce a waveform like that, which would be due to planar diffusion. So you can play tricks and change the response waveform, and in this case, for biomacromolecules, very advantageously so, so that you can quantitate things at low concentration. Just want to close the section on voltammetry by making mention of the fact that there are many different functional groups that compounds, biomolecules, small molecule organics have that are reducible. And examples of those are the ketone, carbon-carbon double bond, carbon double bonded to nitrogen, the nitrogen-nitrogen double bond, and sulfur-sulfur bonds. And if you're interested more in organic electrochemistry, then I encourage you to check out the Handbook of Organic Compounds for an extensive compilation of redox potentials for organic molecules. And with that, I'm going to close out this podcast, and I'll talk about hanging drop mercury electrode and the stripping voltammetry experiments in the next.